Long before Google and the rise of today's tech empires, innovation in the 1900s was driven not in Silicon Valley, but in New Jersey, where Bell Labs, the legendary research and development arm of AT&T, drove groundbreaking advances. AT&T, or American Telephone and Telegraph, was the nation's telephone monopoly for much of the 20th century, controlling local and long-distance service, as well as manufacturing the equipment that kept its vast network running. Its origins went back to Alexander Graham Bell, who patented the telephone in 1876 and launched the Bell Telephone Company soon after. Through mergers, acquisitions, and aggressive expansion, that small venture evolved into AT&T, a corporate giant that came to dominate nearly every aspect of American communication. To sustain and improve this vast system, AT&T created Bell Telephone Laboratories in 1925 by merging its own research division with that of Western Electric, its manufacturing subsidiary that built everything from switchboards to telephones. At its peak, Bell Labs employed over 15,000 people, including more than 1,000 PhDs, making it one of the largest and most prestigious research institutions in the world. Its guiding mission was universal service, the idea that anyone, anywhere, should be able to pick up a phone and connect with anyone else in the world. Bell Labs went on to produce some of the most important breakthroughs of the 20th century: the transistor, Claude Shannon's information theory, the laser, and the launch of the first communications satellites. Part 1. Vacuum tubes. In the earliest days of the telephone, the biggest obstacle was distance. The human voice, converted into an electrical signal, faded after a few miles, even when using the best copper wires and early forms of amplification. At the dawn of the 20th century, long-distance calling meant New York to Chicago, a far cry from the vision of the connected globe. So John Carty, AT&T's chief engineer, and his deputy Frank Jewett visited San Francisco, which was being rebuilt after the 1906 earthquake. They began discussing an intercontinental phone line linking New York to San Francisco, hoping it could be ready for the 1914 Panama Exposition. The obstacle was finding a telephone repeater strong and clear enough to extend voice signals across the continent. Thus, Jewett turned to a physicist by the name of Robert Millikan at the University of Chicago, asking for young researchers who might help. One of his students, Harold Arnold, joined AT&T and began working on improving the Audion tube, which could amplify signals without severe distortion. AT&T had purchased the rights to the Audion, a device which consisted of a light bulb with three main parts. The first of these parts was the cathode, a heated filament that released electrons into the surrounding space. Next came the grid, a thin wire mesh placed at the center of the device, where the voice signals entered the system. Finally, the anode attracted the electrons that made it past the grid. By inserting the voice signal at the grid, the Audion could control the flow of electrons between the cathode and anode. This allowed a weak electrical current carrying the voice to modulate a much stronger current inside the tube, producing amplification that made long-distance telephone calls possible. With the vacuum tube finally tamed, AT&T pressed ahead with its transcontinental project. Engineers installed a series of tube-based repeaters along the new line, each one boosting the voice signal so it could leap from city to city without fading. By 1914, the wires stretched from New York all the way to San Francisco. And on January 25, 1915, Alexander Graham Bell ceremonially placed the first transcontinental call to his old assistant, Thomas Watson. From coast to coast, a human voice had traveled more than 3,000 miles by wire. The achievement was both practical and symbolic. Practical because it proved that long-distance telephony could connect the nation, and symbolic because it marked the beginning of a new era in communication. Yet the system was still expensive and power-hungry, with each vacuum tube fragile and short-lived. Even as the first calls rang across the continent, AT&T's leaders understood that the future would demand something smaller, cheaper, and more reliable. The problem of distance had been solved for the moment, but the search for better technology had only just begun. The transcontinental project proved that the hardest problems in communication could not be solved by tinkering alone. Breakthroughs like Harold Arnold's improved vacuum tube showed the need for systematic research, rigorous testing, and teams of trained scientists. This insight led to the creation of Bell Telephone Laboratories in 1925, when AT&T merged its research and engineering divisions into a single institution. In its earliest days, Bell Labs took shape in New York City, with its main offices at 463 West Street in Manhattan, a massive brick building on the Hudson River. About 3,600 employees from AT&T and Western Electric were brought together under one roof, including engineers like Frank Jewett, who became the first president of the labs, and a growing roster of physicists, chemists, and metallurgists recruited from universities. Unlike an academic lab, where research might end in theory, Bell Labs combined scientific investigation with industrial purpose. Its mission was not only to understand the physics of communication, but to turn that knowledge into devices and systems that could be deployed across the AT&T network. This unusual mix of world-class science and practical engineering defined the culture of the labs from the very start. Part 2. How Shannon and the Transistor built the information age. As World War II broke out and the Nazis swept across Europe, Bell Labs' focus shifted almost overnight. The sprawling research center that had been built to improve telephone lines was pulled into the war effort, redirecting its scientists and engineers toward urgent military needs. In 1941, the labs moved from its crowded Manhattan offices to a new campus in Murray Hill, New Jersey, about 25 miles from New York City. Set amid quiet suburban towns where many executives of its top people lived, the site provided space, secrecy, and modern facilities just as the war effort demanded them. Radar became one of the lab's key priorities. Building on British magnetron designs, this technology could be used for the Allies to track planes in the sky. Its sister technology, sonar, was also advanced at Bell Labs, with the purpose of locating German submarines. Mathematicians at the labs tackled another pressing need: automatic fire control. These were some of the earliest digital computing devices, able to calculate the future positions of incoming rockets and aircraft. These systems proved crucial in defending London against German V-1 rockets in 1944, marking one of the first wartime uses of electronic computation. Bill Shockley, to whom we will return shortly, was part of a wartime research team of physicists, statisticians, and naval officers, analyzing the effectiveness of Allied anti-submarine warfare. By studying data from bombing runs against surfaced German U-boats, the group discovered that depth charges were set to detonate at about 75 feet, too deep to damage submarines caught near the surface. Their key recommendation was to reset the charges to explode at 30 feet, a simple adjustment that increased the number of U-boats destroyed five-fold in just 2 months. Claude Shannon, then a young mathematician, collaborated on PCM, as well as classified work in cryptography. PCM, short for pulse code modulation, was a method of taking an analog signal, like a voice, and sampling it at regular intervals, then encoding each sample as a series of binary digits. Unlike traditional analog transmission, which degraded with noise, PCM signals could be regenerated perfectly, since any slight distortion of a 0 or a 1 could still be read correctly at the receiving end. In terms of his cryptography work, Shannon's research culminated in a classified 114-page opus, completed in 1945, titled a mathematical theory of cryptography. In it, he laid out the fundamental principles of secrecy systems, introducing rigorous methods for creating unbreakable codes and exploring the redundancy of language. English, he calculated, was about 75 to 80% redundant, meaning much of a message could be predicted. Shannon's report was considered so sensitive that it was classified at once and withheld from publication. However, it provided a framework for understanding efficient message transmission, setting the stage for his post-war breakthrough, the creation of information theory. Information theory was Shannon's great post-war breakthrough, published in 1948 as a mathematical theory of communication. In this landmark paper, he generalized the lessons of cryptography and PCM into a universal science of communication. At its core, Shannon's idea was simple but revolutionary. Any message, whether a phone call, a photograph, or even music, could be broken into fundamental units he called bits. Just as physics had reduced matter to atoms, Shannon reduced communication to binary digits, ones and zeros. Before Shannon's discoveries, communication was treated as a craft rather than a science. Engineers built telegraphs and telephones largely by trial and error, without a unifying theory to explain how messages could be sent reliably. Noise and distortion were accepted as unavoidable facts of life. A fuzzy phone call, a static-filled radio, or a garbled telegram were simply the cost of distance. Information itself wasn't seen as something measurable. It was just words on a page, sounds in the air, or images on film. There was no common framework linking these different media. Shannon's work changed all of that. He showed that beneath the surface, every form of communication could be expressed in the same simple language of bits. And while the idea sounds elegant and almost obvious in hindsight, Shannon's 1948 paper was anything but casual. It was dense with rigorous mathematics, filled with equations, proofs, and models that gave his theory the scientific weight to transform engineering practice. It was one of the rare moments in history, an academic would later point out, where somebody founded a field, stated all the major results, and proved most of them all pretty much at once. And thus we return to William Shockley and the creation of the first transistor. While Claude Shannon was busy turning information into something measurable and universal, Shockley and his colleagues were tackling the physical side of communication, how to build devices that could carry, amplify, and control those signals. Vacuum tubes had powered the early phone system and even helped win the war, but they were bulky, fragile, and consumed lots of energy. Shockley believed there had to be something better, something smaller, faster, and more reliable. As early as December 1939, Shockley had already imagined such a device, a solid-state amplifier built from semiconductors rather than fragile vacuum tubes. He persuaded his colleague Walter Brattain to build a prototype, but the experiment produced no results. Before he could push further, the war intervened, drawing Shockley into military research and putting his semiconductor ideas on hold. Joined by Walter Brattain and John Bardeen, they would return to the problem of semiconductors after the war by attempting to create a solid-state amplifier to replace vacuum tubes. Their early results were discouraging, but a breakthrough came when John Bardeen realized that the surface of the material was trapping electrons, and if electrolytes were applied on the materials, a solution to increase conductivity, this barrier could be overcome. In December 1947, Brattain and Bardeen tested a device built around two closely spaced gold contacts pressed against a slab of purified germanium. To their amazement, the setup amplified a signal. A weak electrical input came out stronger on the other side. It was the first working transistor, a point-contact transistor. On December 23, 1947, they demonstrated the device to their colleagues, showing that it could take in a faint signal and make it louder, without the need for a vacuum tube. The invention marked a turning point. The transistor was smaller, more efficient, and far more reliable than tubes, and it would quickly prove to be the building block of all modern electronics. But at that moment, in the quiet days before Christmas, the significance of what Bardeen and Brayton had achieved was known only to a handful of people inside Bell Labs. Shockley, meanwhile, was already thinking about how to reshape their breakthrough into something more practical, and how to ensure his own name would be tied to it. So in the months that followed, Bell Labs refined and improved the transistor. Shockley, frustrated at having missed the glory of the first breakthrough, devised his own design, the junction transistor, which proved far easier to manufacture and soon became the industry standard. The very first practical application came in hearing aids, where the transistor's tiny size and low power consumption made it a perfect replacement for bulky, short-lived vacuum tubes. From there, it spread rapidly into military radios, and soon after, into computers, shrinking machines that had once filled entire rooms down to something that could fit on a desk. What Shannon had done for information in theory, the transistor now made possible in practice. His mathematics showed that all communication, whether words, music, or pictures, could be reduced to bits, while Shockley, Brayton, and Bardeen had given the world a device that could switch and amplify those bits reliably, cheaply, and at astonishing speed. Information theory gave engineers the blueprint. The transistor gave them the machinery. Together, they formed the twin foundations of the information age. Every digital technology that followed, from microchips to satellites, from the internet to smartphones, would rest on these two discoveries: the abstraction of information into bits, and the transistor, which made it possible to process those bits at scale. Part 3. Satellites. John Pierce was not a typical Bell Labs engineer. A scientist, writer, and sometime science fiction author, he had a gift for being in the right place at the right time. Pierce was the last person Shockley spoke to before he began working on the junction transistor. He also encouraged his friend, the author Arthur C. Clarke, to undertake a history of overseas communication. And when Bell Labs unveiled the solid-state amplifier, it was Pierce who suggested the very name transistor, a contraction of transconductance and resistor, giving the century's most important invention its enduring identity. As early as 1954, Pierce began to articulate a vision for communications satellites. He proposed that orbiting unmanned spacecraft could act as relays, bouncing signals from one part of the globe to another. While the rocket technology of the time was not yet capable of launching such devices, and the economics remained uncertain, his calculations demonstrated the potential. He recognized that intercontinental cables were costly and prone to failure, while a network of orbital relays promised greater capacity and reliability, particularly for bridging vast oceans. His ideas gained traction after the Soviet Union launched Sputnik in 1957, jolting the United States into a race for space superiority. Pierce saw an alignment of technological readiness and political urgency, and he pressed for a passive satellite at Bell Labs. He argued that although an active satellite, with its own power and amplification, was more ambitious, a simpler passive reflector, essentially a large balloon in orbit, would be a manageable first step. This cautious strategy became Project Echo, an experiment to test the fundamentals of space communication without the immense development costs of a powered satellite. The launch of Echo in 1960 marked a momentous milestone. A giant mylar balloon, it successfully bounced signals between the United States and Europe. The demonstration was limited but profound. It proved that space-based communication was viable. It also revealed Pierce's gift for foresight and his ability to push Bell Labs toward bold experiments when outcomes were uncertain and economics unproven. Echo set the stage for Telstar, the next leap forward. Unlike Echo, which merely reflected signals, Telstar was conceived as an active satellite, It carried its own electronics: batteries, transistors, traveling wave tubes, solar cells, and antennas, allowing it to receive, amplify, and retransmit signals. Telstar embodied Bell Labs' ambition to move from simple reflection to active management of communication in space. It was a marvel of miniaturization and robust engineering. Its solar cells, also discovered at Bell Labs and once dismissed as impractical for use on Earth, proved ideal in orbit where sunlight was abundant. Its transistors, the revolutionary replacements for bulky vacuum tubes, provided efficiency and reliability. Its traveling wave tubes and masers, Bell Labs' own advanced technologies, amplified faint signals from Earth with exceptional sensitivity and precision. Together, these components made Telstar more than a relay. It was a true spaceborne node, enabling real-time voice calls and even live television transmission. On July 10, 1962, years of research and development culminated in Telstar's launch aboard a Delta Thor rocket from Cape Canaveral. The small sphere, about 3 feet across and weighing 170 pounds, slipped into orbit as the world watched. Ground stations at Bell Labs' Crawford Hill facility in New Jersey and at the Jet Propulsion Laboratory in California were ready to make contact. The first transmissions were historic. Frederick Capell, chairman of the telephone company, placed a satellite call to Vice President Lyndon B. Johnson, a brief conversation that nevertheless proved the feasibility of voice communication not carried by cables. Soon after, Telstar carried the first live television signal across the Atlantic, beginning with an image of the American flag waving at the main receiving station. The achievement captured the global imagination, inspiring not just a hit song by the same name by the band The Tornadoes, but also the realization that a truly interconnected world was no longer theoretical. It had arrived. Epilogue. The twilight of Bell Labs' golden age was as inevitable as the passing of its titans. Claude Shannon, the architect of the digital universe, traded his dazzling work to chase a number of personal curiosities before Alzheimer's dimmed his brilliance. William Shockley, once a pioneer of solid-state physics, spent his later years in the shadow of controversy as a result of his theories on race. John Pierce, the restless instigator, saw his vision of satellites realized, but far from the labs he once called home. The very inventions Bell Labs had given the world, transistors, lasers, fiber optics, digital switching, empowered upstarts to challenge AT&T's empire. Competition soon arrived with a vengeance. Then the antitrust suits returned, first filed in 1949 and revived in the 1970s. These grew into an existential threat. What had once been accepted as a natural monopoly came to be seen as dangerous power. In 1984, AT&T was broken apart into smaller units. The split reshaped Bell Labs, leaving its mission tied to a company struggling to survive in a deregulated, hyper-competitive world. Yet, amidst the fragmentation and the downsizing, its legacy endures. The foundational discoveries made at the labs, the transistor, information theory, the laser, fiber optics, the seeds of cellular technology, are woven into the very fabric of our digital age. Though the grand institution as Mervyn Kelly once envisioned it may be gone, its echoes resonate in every digital signal, every satellite transmission, and every line of code that connects us. The laboratories may have changed, the names on the doors may be different, but the ideas, born in quiet rooms and illuminated by a relentless curiosity, continue to shape our world. The factory of ideas may have closed its doors, but the factory of innovation, inspired by its blueprint, continues to hum. This was The Idea Factory by John Gertner, first published in 2012. Thank you for listening.